Good day, statisticians. Today we're going to continue our study of the relationships, the associations between paired quantitative variables. The relationships we're going to be looking at today are not going to be linear ones, as you might guess just looking at the screen right now. Not all relationships between variables are linear. In fact, we can see an example right here that's clearly not linear. So how do we develop a mathematics to come up with equations for predicting using least squares regression for nonlinear associations? So we're going to get an intuition for that right here, right now. So here we have two variables, very basic, extremely basic, couldn't be more basic, x and y, where x is 1, 2, 3, 4, 5, and y is 10, 100, 1,000, 10,000, and 100,000. And the interesting thing is clearly this is not linear, and if you think about it, it's some kind of exponential association. And it's actually, if you just know a little bit of algebra, it wouldn't be too hard for you to come up with a equation that will perfectly predict a y from x, right? And you might notice, oh, well, 10 is 10 to the first power, 100 is 10 to the second power, 1,000 is 10 to the third, 10,000 is 10 to the fourth, and 100,000 is 10 to the fifth. And it doesn't take too much to say like, oh, look at these x's. Oh, look, the powers of 10 are the x coordinates themselves. So yeah, this equation would be something like y hat, right? Y hat equals 10 simply to the x power. Great, done. Well, yeah, this is pretty easy to come up with, but most of the time, we're not going to be dealing with perfect exponential associations or perfect nonlinear associations. We're going to have residuals for whatever type of equation we create. We're going to have messiness. So it's not going to be as easy as just staring at it and coming up with this nonlinear equation. How do we do that? Well, the interesting thing is, again, we're going to see that we'll ultimately use least squares regression. We're going to, in fact, use a line of best fit to come up with a non-linear equation. I might be like, well, how do you come up with a line of best fit for something that's nonlinear? Well, the key is by taking something that's nonlinear and we're going to make it linear. How do you make something nonlinear linear? Well, hidden inside of this exponential relationship is actually a linear relationship. There is. Like, what are you talking about, Mr. Zach? Let's reveal this, right? And one way to start thinking about it would be to change the scale of my y-axis, right? Here I have just a y-axis that goes up by 20,000s, a perfect linear scale. But what if I was to change the scale of the y-axis? What if I was to use what some people call a logarithmic scale? Well, if I make a logarithmic scale, notice that I'm actually no longer going up by 20,000 each time. I'm going up by powers of 10. In fact, I started off at 1, and then 1 times 10 is 10 times 10 times 10 times 10 times 10. So I have a logarithmic scale, my y-axis. And when I look at this data set on a logarithmic scale, I see, do you see it? A perfect linear association between these variables. So this is a great hint for how we actually can start to use and see a linear relationship hidden within the exponential. Now, we're not going to just change the scale of our y-axis in order to come up with the line of best fit, because it just doesn't work that way, right? We're going to still want to maintain a kind of linear scale on my x and y-axis to come up with a linear equation that'll actually relate x and y here. Now, the way we do that, though, is with sort of the inverse operation of an exponential. And what's the inverse operation of an exponential? It's a log, right? Recall, we started off with the number 10, the number 100, the number 1,000, the number 10,000, and 100,000, right? And if you remember properties of logs and how logs work, right? If I take the log, which is understood to be base 10. Log base 10 of 10, you just get 1. Log of 100 is 2, log of 1,000 is 3, log of 10,000 is 4, and log of 100,000 is 5. And so really, I have this relationship that between x and y, that log of y is just whatever x is itself. And we could see that right here on our graph, right? That in fact, I can say log, right, log of y, but not just log of y, the predicted, right, log of y simply is x itself. right? And that is a perfect linear relationship, not between x and y, but a perfect linear relationship between x and the log of y. Now, the fun fact is that this is, of course, truly a nonlinear association because when there's a perfect exponential relationship, there's going to be a perfect linear relationship between x and the log of your y value. It's kind of neat. You could use this to make predictions. Right now, we don't want to extrapolate too much here, but let's just say I wondered, what will y be, right? What is going to be y hat when x equals, say, 6, right? Now, 6 was just beyond our data set. Technically, that's extrapolation, but this is easy to do. If I said, what's y hat going to be when x is 6? Well, I could predict, right? I can predict that the log of y hat, oops, I put too many hats. There's a hat inside a hat. The predicted log of y is simply going to be whatever x itself is, which is 6. And so the predicted log of y is going to be 6. And then I could take this exponential equation and solve for y. Because that's base 10, I could just do 10 to that, 10 to that. Y hat is going to equal 10 to the 6th power, which is 1,000,000. 1,000,000. There's a perfect linear relationship between x and log y, but that leads to describing a nonlinear relationship between x and y. So this is the fundamental method that we're going to use. Now let's take a look at a data set that's much more realistic and a little bit uglier. In some ways beautiful, though. I don't know if you like movies. I'm a big fan of movies. Not all movies, though, but one of my favorite directors is, oh my gosh, I'm drawing a blank. Christopher Nolan, right? And I picked out 3 well-known Christopher Nolan movies. Some of my favorite movies of all time, in particular, Interstellar and Inception. Fantastic films. And what I was looking at, just for fun, I was looking at some box office results for movies in general, and I noticed, of course, that they always drop off. And so what I did here is I collected information in millions of dollars for the box office sales for these movies from weeks 1 to week 10. I did it for Interstellar, for an Inception, and Dunkirk, and there they all are. And while I have them down in different lines here, I made a scatter plot that shows them all. And voila, here is a scatter plot that shows the box office results for these films all combined. So you could see all 3 of the movies start really, really high, and then they drop off, they drop off, they drop off, but they don't drop off in a linear way. And so it's kind of fun to be looking at this data set. And when I after I pulled this data, I started to wonder, I'm like, I wonder if an exponential relationship would model this. So I started off by just making a linear relationship. When I looked at the linear relationship, you can see in our residual plot, this is no dice, right? This clear evidence. We see positive residuals, negative residuals, positive residuals. This residual plot indicates, yeah, there's no way that we can use a linear relationship to describe these things. But could we use a logarithmic? Now, to use a logarithmic, we'd have to do a logarithmic transformation just to the sales in millions of dollars. And so I use natural log because I prefer natural log to base 10. It's like, I don't know, it's more beautiful in some of our calculus later on in life, so I tend to use natural logs. But here, I simply took the natural log of every single amount of money that was made. So, for instance, the first Inception week 1 was $100.158 million. So if I took the natural log of $100.158 million, I got 4.6067. And so you'll notice right down here that, oh, there it is, 4.6067 is the natural log of that value. So I did that for all of these, all 30 data points. And then I looked at what I got, and voila, what do you see here? It's pretty gosh darn linear. I took that nonlinear association and I linearized it, right? Simply by taking the natural log of all of the y values. And so once I have that, I take a look at my residual plot to detect to see if this really looks linear, and gosh darn, if I don't really see much of a pattern in my residuals at all, I mean, I see a scattering of positive and negative residuals. There isn't a clear like positive, positive thing going on here. This seems to be like a pretty gosh darn good fit. And so as it turns out, the best equation for predicting the gross sales based on the number of weeks that you've been, a Christopher Nolan movie has been out, is based on this nonlinear equation, right? If I go here, I see, if we want to construct this, right, here's the computer output. I start off with my y-intercept, 4.6971, and I'll subtract to that, we've got a slope of 0.4152. This will be times the week that the movie has been out, week 1 through, I wrote week, like week sauce. No. I wrote it right the first time. W-E-E-K, the week number, right? And this won't tell me, as we say, y hat. It tells me the natural log of y hat. This is the best way to predict the natural log. And so I can use this to make predictions all across the board. If I tried to predict like what would happen on week 11, which again is something very problematic. We need to be careful with extrapolation. But if I wanted to predict what might happen in week 11, what would be the gross sales in week 11 for a Christopher Nolan movie based on looking at these three, I can simply plug in 11 for the week, right? And I would multiply that by 0.1452, and I would do 4.6971 minus that result. And that would give me a prediction for the natural log of y hat. Let me do that right quick. Be like, okay, calculator, 4.6971 minus 0.4152 times 11. And I get that number, right? Okay, so 0.1299. Now that is not the gross sales. It's not trying to say that, of course, this would still be in, I guess, the units of the millions if you were to misinterpret this. But this is not the gross sales. This is the natural log of the gross sales. This is the natural log of y hat. So if I want to figure out what that is, let me just solve this little logarithmic equation. Let me solve for y hat. Natural log is base e, so that would mean y hat equals e to the 0.1299 power. And if you're wondering what e is approximately about 2.71 or so. So let me plug that in. I really should be written this someplace where there was more space. If I go to my calculator now, I could say, aha, there's this little e button here, right there where the natural log is. I hit second natural log, gives me the e. I'll just put in that number, and Shazam, 1.1387. So if I had to predict, I'll write this down here, I would predict when y hat 1.1387. This is in millions of dollars. Millions of dollars is how much I would expect a Christopher Nolan movie to gross on week 11 in general, based on the evidence we saw for these first three movies here. So this is kind of how an exponential relationship is going to go between two variables. The key here is that we will ultimately find a linear relationship using least squares regression between x and the natural log of whatever y is, right? Or it doesn't have to be natural log. It doesn't matter what the base is. You could do log 10, log base 2. In this case, I did log base e, natural log. But take the log of all your y's, and then you'll find, if it's truly exponential, a beautiful linear relationship. We'll notice that it truly is linear is once we make a least squares regression line between x and the log of y. We should look at a residual plot and see no pattern, an equal scattering of positive and negative residuals for all of our x values. So that's what we have here. That is an exponential regression. Have at it. Have some fun doing some problems. Have a beautiful day.